Good morning, students. This is Aravind, Assistant Professor, Department of DBSIT, Kavali. So, in the previous classes, I discussed about various tests on DC machines like brake test, Simmons test, Hopkinson test, retardation test, and field test. So, these all tests are performed on some tests are performed on DC motors and some tests are performed on generators also. And now in this class, I'm going to discuss different numerical problems on testing of DC machines. Okay. So firstly, we will get into the first problem, that is. So here they given that a 440 volts DC shunt motor. So here they given DC shunt motor. Okay. So a 440 volts DC shunt motor takes a no load current of 2.5 amperes. So here it does not having the load, it having the no load. Okay, that means in the problem they already given the supply voltage, that is 440 volts, and no load current, that is 2.5 amperes, that is I naught. Next, the resistance of the shunt field and the armature are, so shunt field resistance, that is RSH is equal to 550 ohms, and armature resistance RA is equal to 1.2 ohms respectively, and the full load line current is 32 amperes. This is the line voltage or load voltage, 32 amperes. And find the full load output and the efficiency of the motor. So by using these data, we have to find out the full load output and the efficiency of the motor. So generally this is the basic problem to calculate the efficiency of the motor. So firstly, note down the given data from the problem. So here they given the supply voltage V is equal to 440 volts and no load current, that is I naught or I is equal to 2.5 amperes, and shunt field resistance is 550 ohms, that is RSH, and armature is, this is a shunt motor, that's why I am taking RSH. If it is a series motor, that is RSC. Okay, and the armature, that is the armature resistance, that is RA is equal to 1.2 ohms, and a full load line current is 32 amperes. So either it is IL or IL, that is 32 amperes. So by using this data, firstly we have to find out the output power. So actually from the problem they given that no load current, that is I or I naught is equal to 2.5 amperes, and firstly we have to calculate the input power, that too from the no load. So that's why I am indicating with the no load input, that is the no load input power, that is equal to V into I. So in the problem they already given that voltage is 440 volts into no load current, that is 2.5 amperes, and finally we have the no load input, that is P naught is equal to 1100 watts. And in the problem they given that DC shunt motor, that's why here if you want to calculate the shunt field current, you have to use the formula, that is ISH is equal to V by RSH. You know how it comes, this equation, this is from the Ohm's law. Okay, basic is by Ohm's law. So from the Ohm's law, ISH is equal to V by RSH. So here they given that the voltage is 440 divided by RSH value is 550 ohms, that is shunt field resistance, that is 550 ohms, and finally we have the shunt field current, that is 0.8 amperes. So in a DC shunt motor there is a relation, that is I is equal to ISH plus IA. So I is equal to ISH plus IA. So that is the current in the motor is equal to the combination of shunt field current and armature current. So by using this equation, this formula, we will rewrite this equation as, that is IA is equal to I minus ISH. So if we, from this one we have to calculate the armature current. That's why I am taking IA is equal to I minus ISH. So from the problem they given that no load current, that is 2.5 amperes, substitute here in the I place 2.5 minus ISH, that is the 0.8 amperes. So totally we have the armature current, that is 1.7 amperes. 1.7 amperes. So up to now we calculated no load power, that is P naught, and shunt field current ISH, and the armature current IA, and now we are going to calculate the losses. So if you want to determine the efficiency of the motor, firstly we have to calculate the output power and input power, that too for a full load. Okay, actually they given the no load data, but we want to calculate the full load output power and efficiency of the motor, DC shunt motor. That's why I am taking firstly I am taking no load armature copper loss, and further we have to calculate the full load armature copper loss and like the total losses like that. So firstly we have to calculate the no load armature copper loss. So the formula is, already the armature copper loss formula, Ia square Ra, same taken here, Ia square Ra. So previously we calculated the armature current, that is 1.7, substitute here, so 1.7 whole square into Ra. So armature resistance is already given in the problem, that is 1.2 ohms. Substitute here. Finally, we have the no load armature copper loss, that is equal to 3.468 watts. And next, coming to the constant losses, actually we have the formula to calculate the constant loss, that is constant losses is equal to no load input power, that is the first calculation of this problem, no load input power, that is V into I. So taken here, so no load input minus no load armature copper loss. So this one. Okay, so no load input power we have 1100 watts minus no load armature copper loss, just now we calculated, that is 3.468 watts. Substitute here, we have the value of the constant losses is 1096.532 watts. So 1096.532 watts. And now, so actually we have to calculate the full load. That's why firstly we have to calculate the full load line current. So in the previous case they already given no load current, but here we have to calculate the full load current. So actually now full load line current, that is actually in the problem also they given that the full load line current is 32 amperes. They already given, no need to calculate this one. So right here now full load line current, that is I is equal to 32 amperes. And now you know the relation, that is I is equal to ISH plus IA for a DC shunt motor. And from this one I am writing IA is equal to I minus ISH. So here I is that is full load line current, that is 32 amperes minus ISH value. Previously we calculated that value, that is ISH is equal to V by RSH. So that value substitute here, that is 0.8. So finally we have armature current at full load, that is 31.2 amperes. And after calculating the armature current and then full load armature current, and then we have to calculate the full load copper loss. So same formula using here also, that is Ia square Ra. So here the Ia square is, there is the full load line current or load current. Okay, so Ia square Ra. So Ia square means here we have the value of, that is 31.2 amperes. So 31.2 whole square into Ra value is already given in the problem, that is 1.2. Substitute here. Finally we have the value for the full load armature copper loss, that is 168.128 watts. And next we have to calculate the total losses, because in the previous case we calculated the constant losses. These constant losses are constant for any case, that for no load or full load. Okay, so here I am taking the total losses, that is equal to full load armature copper loss plus constant losses. The combination of full load armature copper loss and the constant losses is called total losses. So here the full load armature copper loss is 1168.128 plus constant losses is 1096.532 watts. Finally we have the total losses 2264.66 watts, that is 2264.66 watts. And next, full load motor input. So that is, already calculated the no load input power of the DC motor, but here we have to calculate the full load motor input, that is V into I. So here they already given that the supply voltage in the problem also 440, substitute here into I value is 32 amperes. That is for full load, not no load. So that is 32. Substitute here, we have the full load motor input is 14080 watts, that is 14,080 watts. And next we have to calculate the full load motor input output. So after calculated the full load motor input, we have to calculate the full load motor output. Why? Because if we want to calculate the efficiency of the motor, we have to know the input power and output power. So already we calculated the full load input power, and next we have to calculate the full load output power. So there is a formula there here to calculate the motor output power, that is input power minus losses. So here we have the input power, that is 14080 minus total losses is 2264.66 watts. Substitute here we have the full load motor output, that is 11,815.34 watts. Okay, next finally we have to calculate the efficiency of the motor. So that is that to at full load. Okay, so that's why we calculate the full load armature copper loss and full load input power and full load output power. And now we have to take the efficiency formula, that is the percentage of efficiency at full load of the motor, that is equal to full load output by full load input into 100. Actually, we have the formula for the efficiency, that is output power by input power, but here we have to calculate for the full load. That's why I'm mentioning full load. So full load output by full load input into 100. So actually we have the full load output power, that is 11,815.34 by full load input power, that is 14,080 into 100. Finally we have the efficiency 83.91. So this efficiency is the full load efficiency of the motor, 83.91. So this is the solution for the first problem. Okay, this is the basic problem. Okay, next, coming to the second problem. So here they given that the no load test. So you know already the no load test, that is the which test? No load test means, so no load test means it is a Swinburne's test. Okay, so here the no load test of a 45 kilowatts 230 volts DC shunt motor gave the following results. So that is input power, input current, that is equal to 14 amperes, field current, that is equal to 2.55 amperes, and resistance of armature at 75 degrees centigrade, that is 0.032 ohms, and brush drop, that is equal to 2 volts, and estimate the full load current and efficiency. Okay, so by using this data we have to estimate the full load current and efficiency of the DC shunt motor. They given that DC shunt motor. So from the problem they given that the data, that is they given supply voltage, that is 230 volts, and the power, that is 45 kilowatts, that is the power, that is 45 kilowatts. And next we have to take the input current, that is 14 amperes, that is for no load. Okay, and next field current they given, that is 2.55 amperes, and resistance of armature, that is 0.032 ohms, and brush drop they given, that is 2 volts. By using this data we have to calculate the full load current and efficiency. So here I mentioned no load current, that is I is equal to 14 amperes, and output power, that is 45 kilowatts, that is the no load power output. So actually I mentioned full load, but it is a no load. And coming to the no load power input, they didn't given in the problem. That's why firstly we have to calculate the no load power input. So you know the formula to calculate the power input, that is equal to V into I, that is the no load current into supply voltage. So in the problem they given that the supply voltage 230 into no load current, that is input current 14 amperes. So substitute here we have the no load power input for the DC shunt motor is 3220 watts. Okay, next, so in case of shunt motors, in the previous problem also we taken this relation. So current I is equal to shunt field current plus armature current. So we already know the values of the current and shunt field current. That's why I am taking the armature current, that is IA is equal to I minus ISH. So in the problem they given that the input current, that is 14 amperes, minus shunt field current they already given 2.55 amperes. 2.5, that is the field current. So field current for DC shunt motor is the shunt field current, that is 2.5 amperes. Substitute here we have the armature current, that is 11.45 amperes. And next, coming to no load armature copper loss. Okay, so similar to the previous problem, here also they given the no load data, but we have to calculate the full load efficiency. Okay, that's why I am calculating the no load input power, no load armature copper loss, like that, constant losses like that. So here no load armature copper loss formula, you know already the formula, that is IA square RA. For a no load we have to take the IA naught square RA. Okay, so that is equal to, previously we calculated the IA naught, that is 11.45. Substitute here, that is 11.45 whole square into RA value is 0.032 ohms. Okay, so after calculating this one, we have the value, that is 4.19 watts, that is a no load armature copper loss. And in the problem they given that loss due to brush drop, that is 2 volts. So but here I have to take the loss due to brush drop, that is equal to 2 into 11.45, that is the no load armature current, 11.45. And finally we have the loss due to brush drop is 22.9 watts. Why I am taking the armature, no load armature current means the brush is connected to the armature. Okay, the brush pair, the set of brushes are connected to the motor through the armature. Okay, so that's why I'm taking the current, armature current, no load armature current, that is 11.45. We have the 22.9 watts. And coming to constant losses, so you know the formula to calculate the constant losses, that is equal to no load input power minus no load armature copper loss minus loss due to brush drop. So in the previous problem they didn't mention the brush drop, but in this problem they mentioned brush drop. That's why I'm considering this brush drop. So substitute here, no load input power already we calculated, that is 3220 watts minus no load armature copper loss, that is 4.19 watts minus loss due to brush drop, that is 22.9 watts. Finally we have the constant losses, that is 3192.91 watts. And now let Ia be the full load current in the armature. Why? Because in this problem we have to calculate the full load efficiency. Okay, that's why I'm taking this one. So firstly we have to calculate the full load motor input, that is I. You know the relation, that is I is equal to ISH plus IA. So by using this one, I is equal to IA plus ISH. So in the problem they didn't mention the current value. That's why I'm taking I is equal to IA plus ISH value they given, that is 2.55 amperes substitute here, and full load motor input, that is equal to V into I. So in the problem they given that 230 volts supply, that is 230 into I value is IA plus 2.55 watts. This is the full load motor input. And next, so motor input, you know the formula to calculate the motor input power for a full load, that is motor input is equal to motor output plus total losses. Motor input is equal to motor output plus total losses. So total losses means nothing but the constant losses plus brush loss plus armature copper loss. Okay, actually we know the motor input, that is 230 into IA plus 2.55. So that is equal to motor output, that is 45,000 plus total losses, that means constant loss we have, that is 3192.91 plus brush loss, that is 2 into IA plus armature copper loss, that is IA square RA. So here I am taking 45,000 plus 3192.91 plus 2 into IA plus IA square into RA value, you know, that is 0.032 ohms. So after simplifying this one, we have 0.032 IA square plus 2 into IA minus 230 into IA plus 45,000 plus 3192.91 minus 230 into 2.55, that is equal to 0. It is coming under the equation. So by simplifying this equation we have 0.032 IA square minus 228 IA plus 47,606.41, and finally we have IA square minus 7125 IA plus 1487700.3, that is equal to 0. This is comes under the equation. So you know the formula to calculate this type of equation, that is x is equal to minus b plus or minus root of b square minus 4ac by 2a. So take that formula here. So here I am taking minus 7,125 here. So that is 7125 plus or minus root of 7125 whole square, that is b square minus 4 into uh, a into c, 4ac, that is a is 1 and c is 1487700.3 by 2. 2 into A. So that is here A is 1, that is we have only 2, that is why we have the armature current, that is 215.30 amperes. Okay, after simplifying this we have the armature current, that to full load armature current 215.30 amperes. And coming to the full load motor input current, so that is equal to 215.30 plus 2.55, and finally we have the 217.85 amperes. This is the full load input current I. Okay, and next full load motor input, that is equal to V into I. In the problem they given that the supply voltage is 230 into current. Just now we calculated the input current, that is 217.85. Substitute here we have the full load motor input is 50,105.5 watts. And next, finally we have to calculate the full load motor efficiency. You know the formula, that is full load output power by full load input power into 100. So the output power of the motor is 45,000 watts. They already given in the problem 45 kilowatts divided by input power, that is just now we calculated, that is 50,105.5 watts. And finally we have the efficiency 89.81%. Efficiency of motor at full load is 89.81%. And next, so this is the solution for the problem number 2. And coming to the problem number 3, so it contains the brake test. Okay, so they given that in a brake test conducted on a DC shunt motor. So here also the brake test conducted on DC shunt motor, the full load readings. So here they given the full load values, that is tension on tight side that is equal to 9.1 kg, tension on slack side that is 0.8 kg, and total current is 10 amperes, supply voltage is 110 volts, speed is 1320 rpm, the radius of the pulley is 7.5 centimeters, and finally calculate its full load efficiency. This is the problem they given. Okay, so you know already the brake test arrangement experimental setup. So on the right side we have the experimental setup, on the left side we have, sorry, on the left side we have the experimental setup, and on the right side we have the belt and pulley arrangement. You know already this one. So on the belt and pulley arrangement, we have the circle, and it consists of the two wires. That means the weights. On the right side we have the tight side, and on the left side we have the slack side, and these two are connected through the handle. Okay, through the handle, and one is connected to the earth. Okay, so that arrangement. So here, firstly they given that the weight on the tight side that is 9.1 kg, and the weight on the slack side that is 0.8 kg, and the already given current is 10 amperes, and voltage is 110 volts, and R is equal to 7.5 centimeters, that is the radius. R is equal to 7.5 centimeters. You know the formula for the shaft torque for the brake test, that is tau SH is equal to W1 minus W2 into 9.81 into R. So here they given the weight W1, that is 9.1, minus W2 is 0.8 into 9.81 into radius is 7.5 centimeters. So this is taken the meters as 0.075, and finally we have the value shaft torque value of the brake test of the DC motor, that is 6.1067 Newton meter. That's why I'm taking the radius value in the meters, that is 0.075. Actually they given the centimeters, that is 7.5, but here I change it to meters, that is 0.075, and finally we have the shaft torque 6.1067 Newton meter, and we have to calculate the output power. So to calculate the output power in the brake test, we have the formula, that is shaft torque into omega. So shaft torque already calculated into, we know the formula for the omega, that is 2 pi n by 60. Take here, and next substitute the shaft torque and these values into here. So shaft torque value 6.1067 into 2 pi into, they already given the speed value, that is 1320 rpm by 60, and finally we have the output power 844.133 watts, and we have to calculate the input power, that is formula is V into I. In the problem they already given the voltage value 110 into, they already given the current value, that is 10, and finally we have the input power 1100 watts, and the percentage of efficiency of the DC shunt motor, that is P out by P, and that is output power input power into 100. So in the just now we calculate the output power and input power. So output power is 844.133 divided by input power is 1100 watts into 100, and efficiency is equal to, finally we have the efficiency 76.74%. Okay, so this is the solution for the third problem. Okay, next coming to fourth one. So here I am taken retardation test. Okay, so they given that a retardation test is made on a separately excited DC machine as a motor. Okay, so the induced voltage falls from 240 volts to 220 volts in 25 seconds on opening the armature circuit, and in 6 seconds on suddenly changing the armature connection from supply to load. Okay, load resistance, supply to a load resistance, which takes average current of 10 amperes, and find the efficiency of the machine when running as a motor taking a current of 25 amperes on a supply of 250 volts. The resistance of its armature is 0.3 ohms, and that of its field winding is 200 ohms. So by observing this one, they given the retardation test. Actually in the retardation test we have to take the set of motor and generator, Okay, so here they mentioned that the DC machine running as a motor. That's why here I am taking the motor. Okay, so here they already given the average current, that is 10 amperes, and we have to calculate the average voltage across the load, but they given in the data the induced voltage falls from 240 to 220 in 25 seconds. That's why I'm taking the average load, average voltage across the load is 240 plus 220 by 2, and finally we have the 230 volts and power observed. So in this one we have to calculate the observed power. It is mentioned with the W dash. So that is equal to V average into I average. So actually you know the formula to calculate the power, that is P is equal to V into I, and W dash is equal to, here W dash is equal to VAV into IAV, that is the average voltage into average current. So here average voltage is 230 volts into uh, average current is 10 amperes, and finally we have the power observed 2300 watts. Okay, and next they given that the times, first time is t1 is equal to 25 seconds and next one is 6 seconds. And w, you know the formula, w is equal to w dash into t2 by t1 minus t2. So I already explained this formula in the retardation test explanation. Okay, so from that one I am writing w is equal to w dash into t2 by t1 minus t2. So w, just now we calculated the w dash value, that is 2300 into t2 value is the given 6 by t1 minus t2, that is 25 minus 6, and finally we have the power, that is 726.31 watts, and they given the stray losses, that is 726.31 watts. Okay, and motor input current, that is IL, they already given 25 amperes. Okay, so just now we calculate the stray loss, that is 726.31 watts, and next we have to calculate the shunt current. So you know the formula to calculate the shunt current for the shunt motor, ISH is equal to V by RSH. So that is equal to, here V is they already given 250 by RSH is 200, that is shunt field resistance, and finally we have the shunt current 1.25 amperes, and we have to calculate the armature current. So armature current IA is equal to, for the shunt motor we know the formula, IA is equal to IL minus ISH. So they already given IL is equal to 25 amperes minus ISH, just now we calculated, that is 1.25. Finally we have the armature current is 23.75 amperes, and coming to armature copper loss, you know the formula, that is IA square RA. So here IA is 23.75, substitute here 23.75 whole square into RA value is they already given 0.3 ohms. Substitute here, finally we have the armature copper loss 169.21 watts. And coming to shunt copper loss, so you know the formula, that is ISH square RSH. So we already calculated the ISH value, that is 1.25. Substitute here, so 1.25 whole square into RSH value they already given, that is 200 ohms. Finally we have the shunt field copper loss, that is equal to 312.5 watts, and finally we have to calculate the total losses. So total losses is equal to armature copper loss plus shunt copper loss plus stray losses. So here the armature copper loss is 169.21 plus shunt copper loss is 312.5 plus 7 stray loss is 726.31 watts, and finally we have the total losses, that is 1208.02 watts. And next we have to calculate the input to the motor, so that is equal to V into I. So in the problem they already given the supply voltage 250 volts into current is 25 amperes. Here the input to the motor is 6250 watts. And next coming to the output of motor, so if you want to calculate the output of motor, we have the formula, that is input power minus total losses. So here the input power is 6250 watts minus total losses, just now we calculate, that is 1208.2 watts, and finally we have the output of motor, that is 5041.98 watts, 98 watts. And finally we have to calculate the efficiency of the motor, that is eta m. So you know the formula to calculate the efficiency, that is output power by input power into 100 in the percentage into 100. So that's why here the output power is 5041.98 divided by input power is 6250 into 100, and finally we have the efficiency of the motor, that is equal to 80.67%. Okay, so this is the solution for the fourth problem. And coming to the last one, that is fifth one. So here they given that the following tests were obtained during Hopkinson test. So here the following results were obtained during Hopkinson's test on two similar machines. So here they given that the armature currents 37 and 30 amperes and field currents 0.85 amperes and 0.8 amperes, and finally calculate the efficiencies of machines if each has armature resistance of 0.33 ohms. So here I given the diagrammatic representation of the Hopkinson test. So here I am taking the generator motor set, and it consists of the currents, armature currents is 37 amperes and 30 amperes for both motor and generator. For the motor, they have the armature current 37, and for the generator they have the armature current 30 amperes, and they also given the field currents for motor and generator. So the field current of the motor is 0.85 amperes, and the field current for the generator is 0.8 amperes. Okay, next they given the armature resistance is 0.33 ohms. Okay, so by using this data, we have to calculate the efficiencies of machines, that is both for motor and generator. So coming to the solution, so already I said that the figure shows the distribution of current in generator and motor. Okay, and let us calculate the losses in case of both the machines, that is for motor and generator. So for motor, armature copper loss, you know the formula, that is Ia square Ra. So in the problem, they given that the motor armature current is 37 amperes. Substitute here, that is 37 whole square into armature resistance they given for the motor, that is 0.33 ohms. Substitute here, and finally we have the armature copper loss for the motor is 451.77 watts. And coming to the field copper loss for the motor, that is the formula is V into I. Here for the motor, that is V into ISH. So that is equal to 230 into 0.85. That is the shunt field current. You have the field copper loss is 195.5 watts, and total copper losses is equal to the combination of armature copper loss and field copper loss, we known as total copper loss. So here the armature copper loss is 451.77 plus field copper loss is 195.5 watts, and finally we have the total copper loss 647.27 watts. And coming to the generator, the armature copper loss is Ia square Ra. So here the armature current for the generator they given 30 amperes. Substitute here, that is 30 whole square into armature resistance, that is 0.33, and finally we have the armature copper loss for the generator is 297 watts. And coming to the field copper loss for the generator, this is the formula V into ISH. So here they given that the supply voltage is 230. Supply voltage is same for both the machines, that is for the motor and generator. That's why here I am also taking the voltage is 230 into ISH value they already given, that is 0.8. So finally we have the field copper loss, that is 184 watts, and here also we have to calculate the total copper loss. So I already said that the formula to calculate the total copper loss is the combination of armature copper loss and field copper loss. So here the armature copper loss for the generator is 297 watts plus field copper loss for the generator is 184 watts, and finally we have the total copper loss that is equal to 481 watts. And next, so for the motor generator, so here up to now we calculated the losses for the motor and generator separately, but in this case we are taking the motor generator set also. So that's why for the motor generator set also we have to calculate the losses. So that is concerned the total copper loss for the set. So total copper loss for the set is the motor copper loss is motor total copper loss plus generator total copper loss. So the motor total copper loss is 647.27 plus the total copper loss for the generator is 481 watts. We have the total copper loss for the motor generator set is 1128.27 watts. And power taken from the supply, that is input power V into I. So here they given that the voltage is 230 into current is 8.65. So finally we have the power taken from the supply, that is input power is 1989.5 watts, and we have to calculate the stray loss for the set. So if you want to calculate the stray loss for this set, we have the formula, that is power taken from the supply, that is nothing but input power minus total copper losses. So here the input power is 1989.5 minus total copper loss for the set is 11 to 8.27 watts, and finally we have the stray loss for the set is 861.23 watts. This is the motor generator set, but we have to calculate the stray loss for each machine, that is for the motor and generator. So here the stray loss for each machine is W by 2, that is a half. Okay, half of the total stray loss for the set. So here the total stray loss for the set motor generator set is 861.23 divided by 2, that is equal to 430.615 watts. There is a stray loss for each machine, that is for the motor and the generator. Okay, next coming to the efficiency of motor and generator. Firstly, we have to calculate the efficiency of motor. If we want to calculate the efficiency of the motor, we have to know the output power and input power. So firstly, we have to calculate the motor input power, that is equal to V into I. So for the motor, they given the supply voltage 230 into current, they already given 37.85. This is the armature current value, 37.85. And finally, we have the motor input power, that is 8705.5 watts. And motor output power, you know the formula to calculate the motor output power, that is equal to input minus total losses. So here the input power is 8705.5 watts minus total loss means nothing but the copper loss plus stray losses. So here the copper loss for the motor is 647.27. Copper loss is nothing but it is the combination of field copper loss and armature copper loss. So that is 647.27 plus 430.615, and motor output power is 7627.615 watts. So this is the input and output powers for the motor. And coming to the efficiency of the motor, you know the formula, eta is equal to output power by input power into 100. So here the output power of the motor is 7627.615 divided by input power is 8705.5 watts into 100. That is equal to 87.61% for the motor efficiency. And efficiency of generator, here also the output power of motor is given as input to the generator. So we already calculated that one. Okay, so the output of the motor is the mechanical power and the input to the generator is the mechanical power. So we already calculated that mechanical power, that is generator input is equal to 7627.615 watts. And coming to the generator output power, we know the formula, that is input power minus total losses. So here the input power is 7627.615 minus total losses, that is copper loss plus stray losses. Here the copper loss is 481 watts plus stray loss is 430.615. And finally we have the generator output power, that is 6716 watts, and percentage of efficiency of generator is eta G is equal to output power by input power into 100. So here the output power of the generator is 6716 divided by input power is 7627.615 watts into 100. So finally we have the efficiency of generator is 88.04%. So this is a solution for the fifth problem. And next we have one more problem. Okay. So here they given that a field test on two mechanically coupled similar motors. So here also we are using the mechanically coupled, but here we are using the two motors with their fields connected in series and with one machine running as motor and the other as a generator, gave the following data. So for the motor, they given that armature current is 40 amperes, armature voltage is 200 volts, the drop across its field winding is 15 volts, and for the generator, they given that armature current 32 amperes, armature voltage is 160 volts, the drop across its field winding is 15 volts, the resistance of each armature is 0.4 ohms. Here the armature resistance for both the motor and generator is 0.4 ohms, and calculate the efficiency of each machine at this load. Okay, here they given the field test, but they given the two mechanical coupled similar motors with their fields connected in series, but here the machine running as motor and other as a generator. Okay, so here the connections and various voltages and currents are shown in figure. So this is the diagrammatic representation of the field test connected on motor generator set. So this is the, on the left side we have the motor and on the right side we have generator, and the motor consists of the armature winding and field winding. So this armature and field winding consists of voltmeter, that is supply voltage 200 volts, and it consists of the motor field winding consists of the ammeter, that is 40 amperes. There is a motor input current 40 amperes and supply voltage across the armature, that is 200 volts. And on the right side we have the generator. So here the generator also consists of the armature winding and field winding. So here the field winding is connected to the motor, generator field winding, and next the armature winding consists of the ammeter. So here the generator input current is 32 amperes and it consists of the voltmeter, that is voltage across the armature, that is 160 volts, and finally it is connected to the load. So this is the diagrammatic representation. From this diagram, I1, that is the motor input current, is 40 amperes and V is equal to voltage across armature, that is 200 volts, and I2 is equal to load current, that is 32 amperes. On the generator side we have this load current is 32 amperes, and voltage across the generator is 160 volts, and RA and RSC, that is armature resistance and field resistance of each machine. So total input, we have to calculate the total input, that is V into I1. So for the motor, V into I1, that is equal to 215 into 40, that is equal to 8600 watts, and output power for the machine is V2 into I2. So that is equal to V2 is 160 volts into I2 is 32 amperes. So finally we have the output power 5120 watts, and total losses in two machines. So here we are considering the two machines, one is for the generator and one is for the motor. So the total losses formula is the input power minus output power. So here the input power is 8600 watts minus output power is 5120 watts, and finally we have the total losses in two machines is 3480 watts, and series field resistance for both the machines. You know the formula R is equal to V by I from the Ohm's law. So take the same here, that is RSC is equal to V by I1. So here the voltage is 15 volts minus 40. So that is finally we have the 0.375 ohms. And total copper loss for the motor and generator is RA plus RSC into I1 square plus I2 square RA. So that is equal to RA value they already given 0.4 plus RSC value is the given 2 into 0.375 into current is 40 whole square plus 32 whole square into 0.4. Finally, we have the total copper loss, that is 1840.409.6, that is equal to total copper loss 2249.6 watts. Why I am taking these two means the series field winding. Actually, the motor consists of the generator field winding and motor field winding. So here the field winding is separated from the generator and it is connected to the motor. That's why I am taking 2 into RSC. Okay, and stray losses for the set offset is total losses minus total copper loss. So already we calculated the total loss, that is 3480 minus total copper loss is 2249.6, and that is equal to 1230.4 watts. And stray losses for each machine I already calculated this one in the previous problem also, that is stray losses for each machine, that is total stray loss by 2. Here the total stray loss is 1230.4 divided by 2, and finally we have the stray loss for each machine is 615.2 watts. And for motor, we have to calculate the motor input. So that is motor input is equal to V into I. So here the voltage is 200 volts into current is 40 amperes, and finally we have the motor input 8000 watts, and armature copper loss is RA plus RSC into IA square. So that is equal to, so here I am taking the motor and generator separately. That's why here I am taking armature resistance, that is 0.4 plus. Here the series field resistance is 0.375 into armature current is 40 amperes. So 40 volts, that is equal to 1240 watts. And stray losses is already we calculated, that is the stray loss for each machine is equal to total stray loss by 2. So from that one we get the 615.2 watts for each machine, that is for the motor and generator. So here the total losses formula, that is total loss is equal to armature copper loss plus stray losses. So here the armature copper loss for the motor is 1240 watts plus stray losses is 615.2, and finally we have the total loss is 1855.2 watts. And coming to the motor output power, so here we have the formula to calculate the motor output power, that is motor input power minus total losses. So here the motor input power is 8000 minus total losses is 1855.2. So that is equal to motor output power is 6144.8 watts. And finally coming to the motor efficiency, so you know the formula, that is motor output by motor input power into 100. So here the motor output power is 6144.8 divided by motor input power is 8000 into 100. So finally we have the motor efficiency 76.81%. And coming to the for generator, so here also we have to calculate the armature copper loss and series field copper loss and total losses and output of the generator and input to the generator. And finally efficiency. Firstly we have to calculate the armature copper loss, that is I2 square RA. So here they already given the I2 value, that is 32 amperes whole square into armature resistance 0.4. So that is armature copper loss is equal to 409.6 watts, and series field copper loss, that is equal to V into I. So that is equal to 15 into 40. So that is equal to 600 watts. And coming to the total losses, so the total loss is a combination of armature copper loss and shunt field copper loss plus stray losses. So here the armature copper loss is 409.6 plus series field copper loss is 600 plus stray loss is 615.2, and finally we have the total losses is 1624.8 watts. And output of the generator they already given in the input to the motor is 5220 watts, and input to the generator, that is equal to output plus losses. So here the input to the generator is 5220 plus 1624.8, that is the total losses. So we have the input to the generator 6844.8 watts, and coming to the efficiency for the generator. So here the generator efficiency is the, sorry I mentioned motor, but here we have to take the generator. So here the formula for the efficiency is generator output power by generator input power into 100. So here the generator output power is 5220 by motor, sorry, generator input power is 6844.8 watts into 100. Finally, we have the generator efficiency is 76.26%. So this is the generator efficiency and motor efficiency for the given problem. Okay, thank you.